Okay. Hello, everyone. Welcome you all to the SPE Turkey section webinar. We have a very experienced guest today. Dr. Mehmet Parlar will give a presentation about sand management techniques. So if you have questions, please type them in the comments. So at the end of the presentation, Dr. Parlar will answer them. I will direct the questions to him. So I would like to first introduce you, Dr. Parlar, briefly, and then he will continue with the presentation. So Mehmet Parlar is currently a sand control advisor at the Turkish Petroleum OTC. He was previously with Schlumberger for 31 years, with 7 years in product development and 24 years in the sand control prior to his retirement in 2020. Uh, a contributor to more than 60 technical papers and chapter in the SPE Frog Packing Handbook. Parlar holds 29 United States patents, and he was recognized as SPE Distinguished Author in 2000 and SPE Distinguished Member in 2007. And he was an SPE Distinguished Lecturer during 2007-8 and the 2011-12 seasons. So Dr. Parlar was elected as the recipient of the 2015 SPE Completion Optimization and Technology Award. He has been actively involved in SPE conferences, advanced technology workshops, and forums as an organizing committee member, technical committee member, session chair, discussion leader, moderator, and speaker. So Parlar has organized various training courses in sand control with more than 300 operating company engineers attending in 2014 alone. He holds BS and degree from Istanbul Technical University and MS and PhD degrees from University of the Southern California, all in the petroleum engineering. So now I give the microphone to Dr. Parlar. Please go ahead.
Okay, can you hear me well?
Yes.
Okay, very good. So I guess I don't know why this is saying sand control. It should have said sand management techniques, but anyway, apologies for that. And so we're going to be, I'm going to be presenting a slightly extended version of presentation that I used to do during sand control courses that we used to teach together with my colleagues when I was with Schlumberger. So it's going to be an overview of sand management techniques. So first, okay, why what's sand control to begin with? And so many sand formations around the world are unconsolidated and prone to sand production as oil or gas is produced. And goal of sand control is to produce the hydrocarbons, whether it's oil or gas or both, without formation solids. Inability to control sand production over the life of the well can be extremely costly, and it can result in plugging of wellbore and or subsea flow lines, surface handling issues, and choke erosion and potential screen erosion if there is a screen. Okay, so this is a very rough classification of sand formations. Rock mechanics people in Schlumberger had put something like this together, and ever since we use it. And so very unconsolidated, zero strength, dry sand is going to be basically unconfined compressive strength of 0. In other words, it already failed. Okay, individual grain. It exists as individual grains. And second column there is showing Young's modulus, and the third column is showing porosity. And Young's modulus of these totally unconsolidated for zones, if you like, is going to be less than 100,000 psi. Porosity typically high, as high as 35%. And the next one in line is very, very weak damp sand. That's wet sand. And UCS can be less than 200 psi, and Young's modulus less than 300,000 psi, and so on. So without going through all of them, if you get into the UCS range of 1500 to 4000 psi, with the Young's modulus of 2.5 million psi, you get into a gray area. Okay, and all the other ones up there are requiring some sort of sand control, and this is now a gray area, meaning you may be able to get away with no sand control. And the next one is sorry, why doesn't this go down? Let me make my screen smaller. I can't make my screen smaller. Can you guys see the bottom of it, by the way? Consolidated. Hello?
No, we can see.
You cannot see. Okay,
Yeah.
so if I exit full screen, I wonder if that's going to do anything. So
Okay.
for some reason, it doesn't show the bottom of it. Okay, all right. So anyway, when UCS is, or unconfined compressive strength, is greater than 4,000 psi, so you're basically in the fully consolidated. Actually, more than 4,000 psi. You're in the consolidated sandstone. All right. Where do we see sanding problems, sanding reservoirs? And these exist all over the world. In North and South America, predominantly Gulf of Mexico, Alaska, Eastern Canada, and in South America, predominantly Venezuela, Trinidad, Guyana, Brazil, Bolivia, etc. And in Africa, typically West Africa, Gabon, Angola, Equatorial Guinea, and so on. And recently, I added Black Sea over here as well, with the finding that you all are aware of, Sakarya field in Black Sea. All right. So what are the completion options in general? Okay, one option is, well, don't put any sand control and manage the sand at surface. Unfortunately, this is not a viable option in many cases, and particularly in deep water and subsea completions, obviously. Okay, and there are screenless completions, and these are basically involving things like oriented perforating, selective perforating, and in situ consolidation, which can be resins, different types of resins, and nanocomposite materials, mineral precipitation, and so on. And there is in situ conglomeration. I don't know why the screen is showing so weird here. But anyway, in situ conglomeration is another method. And there is screenless fracturing, as well as combination of all of these things, okay, or some of these things. And the other one, is the heart of really sand control, okay? And these are sand exclusion methods. And these can be standalone screens, which means you put a filter, a screen, into the well, and screen is doing the job to stop the sand. And we'll come to that in a little bit. And there are expandable screens, and these are screens that are a certain size, smaller size, let's say, when you're running them in. And once you get to target, by some means, you end up expanding the screen. And this means maybe some sort of a mechanical type expansion, or it could be hydraulic type expansion. And there are also more recently what's called shape memory polymers, which are basically doing similar function to the screen. And it's similar to, in some ways, similar to expandable screen. And then the really heart of sand control are gravel packs, high rate water packs, and frac packs, particularly in cage stall completions, by the way. Okay. All right, I'll just touch base with a couple of these screenless completion options, and just to give you an idea. Oriented perforating, what that means is you perforate for maximum perforation stability, that is minimizing the risk of perforation collapse. And typically in horizontal wells, or high inclination wells, this would be perforating the high side and vertically high side of the horizontal well. And in this case, because it's not sand control, you're not expecting sanding, you're trying to prevent sanding, you use deep penetrating guns for perforation with optimal shot density so as to not create cross perforation destabilization. And in addition, you use smaller diameter perforations for better stability of the perforations. If the sand is totally unconsolidated, or it has low UCS, low unconfined compressive strength, in that case, you anticipate that the perforation will collapse in the formation. And what you will end up with is basically the perforation only in the cement and casing sections. So this oriented perforating technique has been successfully used in some cases with unconfined compressive strength in the range 1600 to 2000 psi. And there is an SPE paper by BP guys as well, and that's listed there. And there they mention, for example, 10 wells in 3 gas fields in Trinidad, 6 successful, 4 failures. Okay, not a very impressive success ratio at all. In situ consolidation. So what is this? Again, another one of these screenless completions. This involves injecting chemicals into the rock to glue the sand particles together, okay, through chemistry, right? And these treatments involve multiple stages, pumped typically after a mud acid treatment, a pre-flush, main treatment, and then a post-flush. And main limitations of these systems are, one, ensuring that all perforations are treated, because all it takes is one perforation, one or two perforations not being treated, and you're back to producing sand, right? And most importantly, sensitivity of unconfined compressive strength and retained permeability to post-flush volume. All right. This is from an SPE paper by Halliburton guys, for example. Okay, and what it is showing is laboratory experimental results, and it's showing what the unconfined compressive strength of the core is if the overflush is 3 pore volumes, 6 pore volumes, or 9 pore volumes. Okay, as you can see, the higher the overflush volume, the smaller the unconfined compressive strength. And what you want is high unconfined compressive strength. Okay, so this is bad news, right? And I'll explain why it's bad news in a little bit. And you look at the retained permeability as a function of, again, pore volumes of overflush. And as you increase the volume of overflush, retained permeability is increasing, which is a good thing. Okay, so this part is good, but this part is bad. Now, if you consider, let's say, 3 feet of penetration in a 12.25 inch wellbore, let's assume 20% porosity, and pore volume is 7.58 cubic foot per foot. If you inject 3 pore volumes of post-flush, that corresponds to 3 times that number, roughly 23 cubic foot per foot. And if you consider a 1 inch ring of formation right next to the cement, the pore volume of that 1 inch ring is 0.055 cubic foot per foot. And if you inject 3 pore volumes of post-flush based on 3 feet penetration, this means the first inch of that formation has seen 413 pore volume. So what does that say about this part? It says the first inch is hardly going to have any strength. Okay, so dependence of these resin treatments to volume of overflush is the basically most critical part of this resin consolidation, making them quite unattractive, to say the least. All right. Let's move on to mechanical sand exclusion techniques. These involve either screen only or screen and gravel. And sometimes people use the term proppant, and in fracturing, typically the term is proppant. In sand control, typically it's gravel, but these are interchangeable. Okay, so I'll use that term interchangeably. All right, let's go over the screen only completion first. In these cases, let's say it's a case tool, which we don't recommend running standalone screen in a case tool. So it's a bad example. Let me use open hole. Open hole is an example. Let's say you got an open hole and you run your screen in and you set your, you do some cleanup treatment, etc. possibly, and you set your packer and so on. And you had sized the screen to stop the formation sand. We'll come to that in a little bit, what that may mean. And the screen can be one of these different types of screens that are being shown. In general, wire wrap or direct wrap type screen, which has a slot type geometry. If you open these wires, this thing, this cylindrical thing, and if you open it, cut it, open it, as it becomes a rectangle, and so the openings between these wires are like this, a slot geometry. And there are metal mesh type screens, sometimes called premium screens. And these screens have mesh type or pore network type geometry. And there are also pre-pack screens, which use typically a wire wrap screen, another wire wrap screen that's larger diameter outside, and in between to the two wire wrap screens, you fill that space with gravel. And these are called pre-pack screens. Okay, not much in use these days, and it's been a long time since I had seen any pre-packed screen completion, to be honest. Okay, so it's either going to be metal mesh type screen or a wire wrap or direct wrap type screen. All right. Then in the screen only category, there are compliant expandable type screens. And the expandable screen, for example, one of them that you'll be looking at here, is such that, so you got a base pipe, and outside the base pipe, filter media, and outside the filter media, a shroud. And when you expand it, before expansion, the base pipe slots are essentially closed. Once you expand it, slots are opening up, and the filter media is basically sliding over each other and keeping it as pore size everywhere. Okay, so this is one type that is mechanically expanded, and there is another type that is hydraulically expanded. And without going into too much detail, it's essentially doing the same thing, meaning it expands. At the beginning, it's small size, and once you get to your target, you pump some fluid, and you expand the screen. And the screen goes to the formation. All right. And there are also what's called shape memory polymers. And these things also somewhat compliant. As long as you are within their range, they are compliant. They expand to the formation. And this is essentially, again, small size when you run it in. And then after you run it in with temperature and pumping fluid, pumping of fluid, the polymer expands and reaches the formation. All right. When we get into now the screen plus gravel, what you're doing is essentially installing a screen just like before, and then pumping gravel in a carrier fluid and filling the space between the screen and either casing or open hole with gravel. So obviously this does not apply to cases where you have expandable systems, expandable screens and things like that. So screen can be wire wrap, metal mesh, or any of these with shunt tubes. And the carrier fluid for gravel packing can be water-based or oil-based. It can be low viscosity or high viscosity, and so on, depending on what technique you're going to use. This keeps moving. Okay. And pumping of the slurry can be either below fracturing pressure or above fracturing pressure. If it is below fracturing pressure, it's called gravel packing. If it is above fracturing pressure, high rate water packing or frac packing. Now, the gravel typically is a synthetic material these days, and such as ceramic, with higher sphericity, permeability, etc., than natural sand. Gravel, in this case, is sized for formation sand retention. Screen is sized for gravel retention or formation sand retention. And the latter allows contingency in case of exposed screen. In other words, if you get an incomplete pack for any reason, or if you have destabilized gravel pack, in that case, sizing the screen for sand retention instead of gravel retention gives you more contingency in terms of keeping the sand in the annulus between screen and open hole or screen and casing. Okay. So when you're pumping these things, this slurry, etc., there are service tools that every service company has. And these service tools have a crossover port or crossover tool. And the way you pump your slurry is you pump it down to drill pipe, down through the drill pipe. And below the packer, the gravel packer, there is the crossover ports. And the slurry comes out of the crossover ports and goes through the annulus between the screen and, in this case, casing, and leaks off into the formation, the slurry, and the fluid. And as the fluid goes there, gravel goes with it. And so then you fill the perforations and something behind, whatever space is available behind. And sorry, this keeps moving. I'm not used to this. And then you pack the annulus as well. So you end up packing the perforations and the annulus, depending on what fluids you're using, etc. For example, if you're using a low viscosity fluid, the packing of the annulus happens bottom up. You start the bottom section packing and then continue on to upper sections. Okay, and this is the natural process. All right, and the gravel is left in that annulus, but the fluid gets into the screen, and in the screen there is what's called a wash pipe, another pipe. And once the fluid gets into the screen, it gets into the wash pipe and goes up in a circulating gravel pack and gets to the crossover again. And in the crossover, it crosses over, the fluid crosses over to the annulus between the drill pipe and the casing above the packer. So slurry goes down in the drill pipe, goes down the annulus, packs that area, and fluid is coming back through this wash pipe and goes up the annulus and comes to surface. When you want to reverse out excess gravel, which typically you have excess gravel that you're pumping for various reasons, and when you want to reverse out, you change the tool position to the reverse position, and what you pump is basically the fluid from the annulus between the pipe, drill pipe, and casing down and through the ports going into the drill pipe, and so you pump the excess slurry back to surface. Okay. Sizing screen for formation sand. What does that mean? And if all the sand particles were the same size, there would be no issue, right? So if everything is the same size, and if the screen has the same openings everywhere, well, you know exactly what to do. And any screen opening smaller than that size is going to do it. But unfortunately, that's not what we have. Typically, we have, well, not typically, always we have a size distribution. So here's a particle size distribution for some real formation sample. And in those cases, what people have shown a long time ago, Coverley and Rogers, for example, that sizing the screen to D10, what D10 mean? It means when you look at the cumulative size distribution, where the size is increasing to the left, by the way, not to the right, okay? And the 10th percentile that you pick here, and that intersects the cumulative curve, and you go down, and that's the D10. That is 10% of the particles by weight are greater than this size. So if you size the screen to that size, which is most commonly used, by the way, and then the transient sand production, by the time sand production stops, would be small. Okay? And more recent work by Schlumberger and University of Texas Austin, as well as Schlumberger Sand Control Client Advisory Board members, have treated this problem through Monte Carlo simulations, randomly picking particles, etc., and dropping them onto the screen. And analytical expressions demonstrated the importance of larger sand particles in sand retention. In other words, to some extent, justifying this using D10, the larger particles, to size the screen. How do you size the gravel for formation sand? And most commonly used criteria in this case is what's called Saussuyer's criteria. And Saussure had done some experiments back in 1974 and published a paper. And basically what he did was use different size gravel and different size formation sand, and doing all these things several times. And he comes up with a curve like this, where what you're looking at is the gravel size, particle size, divided by the formation sand size. In both cases, he is looking at the 50 percentile. 50 percentile of the gravel, 50 percentile of the formation sand. Take the ratio, that's what this x-axis is. And original permeability of the gravel divided by, after you do the sand retention testing, and by injecting sand through the gravel pack, and the ratio of these two is given here. So ratio of 1 means the permeability of the gravel pack is essentially unaffected by the sand injection, meaning those sand particles do not invade the gravel pack significantly. And after some time, which 5 to 6 times the formation D50, when you use the gravel size like that, the permeability starts declining. Okay, and then you start essentially blocking the gravel pack pore space with formation sand, and the permeability is therefore going down. If you make it large enough, gravel, then this thing comes back again, because now you don't have sand control anymore. Okay? All right. So let me skip this one for now, unless you have any questions later on. In case stall completions, one of the most critical things, in fact, the most critical thing is putting gravel into the perforations. Okay, and this slide is just to show the significance of this. And we're looking at basically, let's say, an open hole and a case stall, and the open hole, all right. In the open holes, and first of all, what we're looking at is a 50-foot vertical interval, 1 Darcy formation, 8.5-inch hole, and if it is cased hole, we're using 12 shots per foot and 0.75-inch perforations only in the casing and cement. In other words, in the formation, you don't have perforation anymore because perforations collapsed. It's unconsolidated sand. All right. If you do an open hole completion here, in this case, with a certain tubing size, I don't remember what the tubing size was here, but with a certain tubing size, the open hole gravel pack with 100 Darcy gravel gives you a production rate of 10,000 barrels per day. A standalone screen, if you put a standalone screen and you form a natural sand pack having the same permeability as the formation in that annulus, in other words, filling that annulus with formation sand, you get basically the same production rate, 10,000 barrels per day. And so from a production standpoint, purely production standpoint, these two are no different. You go to cased hole and you do a cased hole gravel pack and fill the perforations with 100 Darcy gravel, the base case scenario in the cased hole case, and your production is down to about 6,500 or 7,000 barrels per day, down from 10,000. And if you put a standalone screen or an expandable screen, in other words, no gravel in the perforations, and in that case, basically, perforations end up filling with formation sand during production, and your productivity goes down to 4,500 barrels per day in this case. Okay, so it's a significant reduction. So put gravel in the perforations in cased holes, and standalone screen or expandable screen in a cased hole, certainly not the best choice. And this is referring to producers in particular. Okay. So when you compare frac packs versus gravel packs versus high rate water packs, this did not turn out very well in this slide show right now, but believe me, there were different colors and things like that here, and it looked a lot better. When I send you the slides, I mean, you'll have the slides later. Okay, so what this is showing is basically looking at a bunch of papers published on the topic and using the data from those papers. Okay, and this is Ratables and ex-Lumberjay guy who did this. And essentially taking the skin numbers from these papers, if it is gravel pack, frac pack, high rate water pack, etc., and putting them together. And flow efficiency here is defined as natural log of RE over RW divided by skin plus the same term. Okay. And so essentially, Ray used ln RE over RW being 8.5. So it's 8.5 divided by skin plus 8.5. Okay. So that's what this axis is. And y-axis is the cumulative probability of getting a completion with a flow efficiency that is higher than a certain number. For example, if you take a flow efficiency of 30%, go vertically up, where this intersects the gravel pack curve tells you 60%. Where it intersects the high rate water pack curve is 75%, and the frac pack curve is 85%. Okay, maybe a little more. But anyway, the bottom line is, if I take this number, 60% number, for example, that says that gravel pack gives a flow efficiency greater than 30%, which means a skin factor less than 20, 60% of the time. Whereas high rate water pack does the same thing 75% of the time, and frac pack 85% of the time. So this is purely statistical. Okay, without looking at into any details, etc. What goes this, what goes that, don't question anything, right? Just purely statistical. All right. Another ex-Schlumberger, ex-Chevron guy, Dave Norman. And he had a distinguished lecture as well on the similar topic and a different time. And he looked at 275 wells, and some of them were Chevron wells, some of them outside his company at the time he did this. And here are some of his results. Skin of less than 20, he says frac packs 96% of the time. High rate water packs 85% of the time. Gravel packs 60% of the time. So his numbers here seem to be a little bit higher compared to what Ray's numbers were showing, at least for high rate water pack and frac pack. Okay. And similar here for skin of less than 5, etc. Okay, I will skip that one as well. Maybe not. Maybe we have a few more minutes. This one, this is again from Dave Norman's DL presentation. And gravel pack skin, frac pack skin, high rate water pack skin. And so these are gravel pack, high rate water pack, and frac pack. And in this case, he put it as KH versus skin. So to have a reference anytime you want to compare based on industry experience, etc., where is our completion standing, for example, and so you can use these things as a baseline or benchmark. There is a lot of variation, as you can see, by the way. Okay. All right. To sum it up, K-stall sand control. Screenless completions have not had an impressive track record in K-stalls. And by the way, you can't use screenless completion in open holes. And screen-only completions at best yield low productivity wells due to sand-filled perforations and often result in screen erosion and thus sand control failure. And frac packs have the highest probability of achieving high productivity in K-stalls, followed by high rate water pack at or above frac pressure, and gravel packs below frac pressure. Okay. Open hole sand control. Screenless completion techniques are not applicable in open hole. Wellbore stability, remember, wellbore stability requires presence of the filter cake to maintain overbalance. And whereas placement of consolidation chemicals requires absence of the filter cake because you want to inject these things into the formation. So there is a contradiction there, right? And so they are not used at all. Frac packing in open holes also has been very limited, with only 3 documented cases, and they are listed here. And in West Africa, actually, after they wrote their paper, this is ExxonMobil, and they ended up doing, to the best of my knowledge, 20 plus open hole frac packs there as well. And both screen only and gravel pack completions have been successfully used in open holes. So I hope this gave you a bit flavor of what sand management, sand control is about. So thank you for your attention, and I'll open it for questions.
Okay. Thank you very much for the enlightening presentation, Dr. Mehmet Parlar. I checked the comments. Actually, there is no questions here, but I have some.
Okay.
So you didn't talk about flow rate. I mean, is there any flow rate optimization or flow rate limitation for the sand control, or you produce as much as you can and then you use the sand control techniques?
Sorry, I'm not clear on the question. Is your question more along the lines of if you have sand control, what is
is there any
there is a
limitation about
sand-free,
the...
there is a sand-free rate, what is called. I think that's probably what you're asking. So
Yes,
if
actually,
you produce at low enough rate, okay, then you won't be transporting, if the sand already failed, by the way, you won't be able to transport the sand, and therefore there is no sand coming. So that's called the sand-free rate. But that rate typically is so low that it's not something where you want to go to. Not worth it.
Actually,
So if it's a very, very low productivity well, and you're producing 10 barrels a day, there are wells like that, by the way, in places, some places. I've been to one of those places in China, the oldest field in China, Dacheng field. Okay, I mean, they are producing like 5 barrels a day, 10 barrels a day. Okay, and I mean, it's government funded, right? I mean, there is no economics. Okay, and so
actually,
yes.
the question was about the flow rate of the well. I mean, if you have high flow rate and the well productivity is good enough, and then at high flow rates there is a turbulence flow at the sand phase, and then it starts to the sand particle starts to transport. So if you optimize this flow rate, then maybe you can keep the sand content at limitations. I don't know if there is any optimization about the flow rate of the well to prevent the sand production.
I thought I answered that, but let me go back. So there is a sand-free rate.
Okay.
For every formation. Okay, so you can do a test if you like, and during the test you keep bumping up the rate, and at some rate you're going to be producing sand. As long as you stay below that number, okay, yeah, you'll be fine. But this is something that's done typically, in, again, low rate environments, very low rate. Okay, but
now
can
I
you do it
understand.
like that? Yes.
Okay, thank you. So the next question is, if it is not confidential, I wonder what's your expectation about the Black Sea in terms of sand production, and which type of sand control technique would work more efficient there?
I mean, those of you who are in the team should be, are already aware, and I'm a consultant for TPOTC. So I am not at liberty to discuss anything that's not in public domain already.
Okay, no problem.
So that part, even though it's a very straightforward answer, and even though we know exactly what we're doing right now, and I cannot disclose anything unless there is somebody here in the audience who can do that. Okay,
no problem at all. Okay. And I think, the audience have some questions. Joshan, I am, in case of, case of gravel packing failure, can anything be done for remedial action?
Depends. If the keystone gravel pack fail means basically getting rid of, producing sand. Is that what you mean by failure, or is it productivity failure, or both? Which one? Sand control failure.
Both.
Is it sand control failure, Joshan?
Let's answer for both.
Let's assume sand control failure. Okay, that he means. Okay, meaning screen ended up, let's say, eroding for whatever reason, and now you're producing sand through that screen. So, in general, you can go down and identify where that happened. Okay, and put some sort of an insert screen. Okay, so that's a possibility. People have tried also consolidating that particular section. Okay, and I don't know how much success they ended up having and so on, but insert is probably one way of going about it. Insert screen, which means your ID is going to be reduced further, right? Because you're putting another screen inside the existing screen. Okay. And in terms of pumping gravel and things like that, no more, none of that. And the other, even obviously costly option is pulling the completion out and redoing things. And so, with deep water, subsea, not done much. Okay. Maybe sidetrack may be a better option in that case. Okay. So, Joshan, we can discuss this later if you wish.
Okay, thank you. So I think there is one more question. So what is the target radius area for consolidation process? So, and does a reperforation required later on?
For the consolidation, target area is, typically numbers that people use are on the order of 2 to 3 feet away from the wellbore. And again, I'm not much of a fan of consolidation systems. The idea is great. Okay, and as I mentioned, referred to one of the papers as well for laboratory data. All the consolidation systems that I'm aware of are sensitive to volume of overflush that goes in. Okay, and the example I gave, if you're doing these things based on 3 feet per volume of 3 feet section, the near the wellbore, those sections are seeing a lot more, and therefore your strength is going to nothing. And so anyway, your question was, what's the target? Typically 2 to 3 feet, but I would not consider this as a primary option. Look at everything else first, and you couldn't find anything to fix your problem, then consider consolidation. That with the hope that you may get lucky.
Okay, I think we come to the end.
Okay.
So Dr. Mehmet Parlar, thank you very much for having time with us. So we appreciate your efforts and your experiences. So and thank you to the. I would like to express my gratitude to the audiences, and let's keep in touch in the next SPE Turkey section webinars. Thank you very much. Have a nice day.
Very good. Thanks a lot for the invitation. Thank you, guys.